Now let's talk about the ionization energy, which is the energy required to remove one electron from the valence shell of isolated gaseous atom. Valence shell is the outermost shell that can have at least one electron. Ionization energy results in generation of cations. We can determine the energy that is required to remove one electron from the valence shell of an atom by converting it into the gaseous state. Because in the gaseous state, we suppose that the atom is free from external forces. For example, if we give energy to magnesium atom, it loses one electron, becoming magnesium positive ion. Magnesium is losing one electron. The energy given to it is the first ionization energy. But magnesium can lose two electrons. So when the energy is given to magnesium positive cation to lose its second electron, it becomes the second ionization energy and magnesium becomes Mg2 positive cation, a divalent cation. The first ionization energy is least, while the second ionization energy is higher than first, and third ionization energy is still higher than second and first. This is because the first ionization energy is the energy required to remove electron from neutral atom, while the second ionization energy is given to the atom in ionic form. When magnesium is in the form of Mg positive, it has lost one electron from its valence shell. The hold of nucleus to the outermost shell increases as the positive charge dominates. To remove the electron from already positively charged species is difficult. Therefore, the second ionization energy is higher than first one. The same is the case with third ionization energy. The ionization energy is determined in electron volt per atom, which is equal to 96.48 kilojoule per mole, and which is still equal to 23.06 kilocalories per mole. The factor operating behind the ionization energy is effective nuclear charge, which is equal to Z minus sigma. Z is the atomic number and sigma is the screening constant. The screening constant is determined by the shielding effect. As the ionization energy is the energy required to remove electron from the valence shell, the electrons are removed from the valence shell, which is the outermost shell of an atom. There are the electrons between nucleus and the outermost shell. When the nucleus has strong control on the valence shell, it becomes difficult to remove the electron from the valence shell, and the ionization energy increases. This holding of the nucleus on the valence shell depends upon the number of electrons between the nucleus and valence shell. These electrons between the nucleus and the valence shell are known as the intervening electrons. Greater the number of intervening electrons, less the hold of nucleus on the outermost shell and less will be the ionization energy. If the shielding effect is low, the number of electrons between nucleus and valence shell are less, and the valence shell is closer to the nucleus, is strongly held by the nucleus, and it becomes difficult to remove the electron from the valence shell, and the ionization energy increases. Let's determine the effective nuclear charge of certain atoms. Consider the second period. Lithium has 3 electrons. Its electronic configuration is 1s2, 2s1. Z is the number of electron or proton, which is equal to 3. Screening constant is determined by the electrons other than that of valence shell. The valence shell of lithium is 2s. The number of electrons between 2s and the nucleus is that present in 1s, which are 2 in number. So its screening constant is 2. Effective nuclear charge is Z minus sigma. 3 minus 2 gives the answer of 1. The element next to the lithium is beryllium, which has 4 atomic number. Its electronic configuration is 1s2, 2s2. Its valence shell is also 2s. The intervening electrons between 2s and nucleus are that present in 1s only, which are 2 in number. The screening constant is 2. Effective nuclear charge is 4 minus 2 equals to 2. And the element next to the beryllium is boron, Its electronic configuration is 1s2, 2s2, 2px1. Its atomic number is 5 and its screening constant is 2. Keep in mind you have to consider the electrons other than that present in the valence shell, and the valence shell of boron is 2, which involves 2s2, 2px1. Valence shell is 2, while the intervening electrons are present in 1s orbital, which are 2 in number. Effective nuclear charge is 3. 5 minus 2 equals to 3. Now you see that as we move from left to right in a period, the effective nuclear charge increases, screening constant or shielding effect remains the same. Now what about the element present in a period? The element below the lithium is sodium, which has atomic number 11. Its electronic configuration tells us that it has one electron in its third valence orbital. The intervening electron between 3s and the nucleus are 2, 4, 6, 8, and 10. The screening constant is 10, atomic number is 11, and effective nuclear charge is 1. The element below the sodium is potassium, which has 19 atomic number. Its valence shell is 4, and the number of electrons between 4s and the nucleus are 2, 4, 6, 8, 10, 12, 14, 16, 18, which are equal to the screening constant. So atomic number is 19, screening constant is 18, and effective nuclear charge is 19 minus 18, which is equal to 1. Along the period, effective nuclear charge increases. The hold of nucleus on the outermost shell also increases. And we say that ionization energy while moving from left to right in a period increases. But the ionization energy of boron is less than beryllium. According to Hund's rule, the orbitals which have completely filled or half filled orbital are stable. In boron, there is only one electron into px orbital. If it removes that electron, its 2s orbital will be completely filled, which is stable according to Hund's rule, and every element tends to get stability. So boron easily loses that one electron. On the other hand, beryllium contains 2s electrons, and which is stable according to Hund's rule. So beryllium does not loses any of its electron from its valence shell easily, because if it loses that electron, it will become unstable. So the ionization energy required to remove one electron from beryllium will be higher than boron, because in the case of boron, the loss of one electron from 2px orbital is favorable, while the loss of electron from 2s orbital of beryllium is not favorable. While moving down the group, the ionization energy decreases. Why it decreases? Though the effective nuclear charge remains constant, but the number of intervening electrons increases. When you move down the group, a complete orbital is added. The valence orbital in lithium is 2. For sodium, the valence shell is 3. For potassium, it is 4. While moving down the group, a complete shell is added. And by the addition of a complete shell, the atomic size increases. As the size increases, the ionization energy decreases. It becomes easier for the atoms to lose the valence shell electron. Now let's talk about the certain factors which can influence the ionization energy. First of all, the effective nuclear charge is directly related with the ionization energy. Greater the effective nuclear charge, greater will be the ionization energy required to remove the electron. When the effective nuclear charge increases, the hold of nucleus on the outermost shell increases and the ionization energy increases. We have to give the greater amount of energy to remove the electron. The second factor is the size of atom. Greater the size of atom, smaller will be the ionization energy. as I have discussed previously. While moving down the group, the size of atom increases, the ionization energy decreases. Now, what about the shielding effect, which is the third factor that can influence the ionization energy? When the shielding effect increases, the size of atom increases. Whenever a complete shell is added, the number of intervening electrons goes on increasing, which are actually causing the shielding effect. And when the shielding effect increases, the hold of nucleus on the outermost shell decreases and it is easier for the electron to be removed. So by increasing the shielding effect, the ionization energy decreases. The fourth factor that can influence the ionization energy is the penetration of valence electrons. Greater the penetration of valence electron, greater will be the ionization energy. As you know that 4s orbital was filled before 3d orbital, but the outermost shell was 4, though 4s was filled first. But the removal of electron will be from 4s first because it was the valence shell. But that orbital is penetrated into the third orbital. So greater the power of penetration of orbital, greater will be the ionization energy. The last factor that can influence the ionization energy is the nature of orbitals. According to Hund's rule, the half-filled and partially filled orbitals are stable. So for the orbitals which are completely filled or half-filled, the ionization energy is less, as you see in the case of boron. The general trend of ionization energy is that it increases along the period from left to right as effective nuclear charge increases, and it decreases down the group as the size of atom increases and shielding effect increases.